Okay, let's get started. So administrative comments. We are slowly catching up with grading of your quizzes and exams, and we think that, and in fact, some of those quiz scores have been pushed to your repositories, and we think that you're going to be extremely disappointed. Yeah. So here's my response to that. We're going to remedy this. We're going to remedy it by looking at the data and figuring out exactly, how to weight things so as to reward you for the learning that you're doing. I don't know how that looks for sure because we haven't seen all the data yet, and Wade and I have not, we have not had time to be in the same room to actually discuss it. But again, I think I've said this before. We are very concerned with being fair. We're concerned with two things. We're concerned with you learning a ton and being fair in the grading. And I feel bad asking you to continue to trust us, but yet I know you're safe in doing so. So I want you to trust us that we're going to get the calibration on these quizzes and exams correct at some point. And I just don't know what that looks like yet. I think the way to think about it from your perspective is that there will be curving and it will be in your favor. Whether it's a curve or, I don't know what that looks like, or we're going to cancel a bunch of stuff or give you a maximum of some stuff. I don't know what that looks like, but it will be in your favor. So, are there any specific questions about administrative issues? No, nothing? Okay. What? Yeah, we're going to learn about trees. Yeah? If we think one of the auto grade, for the labs, if we think the auto grading is incorrect, you think, you should post to the Piazza. Oh, I should say that. You did? I know, we're just way behind. We'll get there. All right, so the right way to contact us with grading concerns is by posting to the Piazza. You can do it privately if you like. Hey guys, shh. Thank you. Wow, thank you. So if you feel like you want to get our eyes on your concerns, post to the Piazza. What happens is course staff answers what they can, and they elevate the things that we need to see. So, and if you feel like we're not answering fast enough, ask again, because our intention is certainly to address all of your concerns. All right, yeah? How many problems of the day are there total? There's going to be about 50 by the end of the semester, okay? We're going to keep going with it, yeah. And I think slowly but surely we're trying to align them a little more closely with the exams so that the programming exams will be like mixing of the problems of the day. There'll be kind of a synthesis of problems of the day. We're aiming toward that. All right, any other administrative questions? I'm acutely aware of the fact that the drop deadline is coming, so I want us to have a pretty good evaluation for you by that point. Yeah, Neil? Answers to the problems of the day. You guys are free to discuss. So I think we're not going to post answers to the problem of the day, but you are absolutely free to discuss your approaches on Piazza. We're certainly not going to say, hey, stop talking about it, because we want you to learn from each other too. But we're not going to post answers to the problem of the day. All right, anything else? Yeah? So here's how I feel about that, okay? I feel like, so the question is, could we post all the past problems of the day so that you can use them to study for? And what I think that will encourage is waiting until right before the test to do about 20 of them. And I don't feel like that's the best way to use them to learn. But I'll think about it. Okay? All right, anything else? All right, let's talk about today's stuff. I'm very excited because, again, it's another data structure. We'll talk about the ADTs, the abstract data types, for which this data structure is useful a little bit later on. Right now we're talking about some math, specifically some combinatorics, and some implementation. So we're very much more on the side of the structure side of things rather than the application side. Okay, so Don Knuth, who was one of my computer science professors when I was in college, I didn't understand that I was in the presence of greatness. I'm just like, oh yeah, my prof, you know. Turns out he's kind of a special guy. Called trees the most important nonlinear structure in computer science. Now, I think at this point you have had exposure to trees in your discrete math class at least, possibly other places as well. So I want to kind of find a conversational way of revisiting some of that material. Oh, hi. Thanks. So to achieve that, I want to ask you to characterize trees for me, but I'm going to start us off. I'm going to start us off by recalling that trees are just graphs, and when I say graph, I mean a graph G is a set of vertices together with a set of edges. Okay, so when I refer to a graph, I mean this mathematical structure, which is just a set of vertices together with a set of edges. And when I say set, I mean the mathematical notion of a set. All right, so what I want to know is what's special about a tree. It's a graph, but it's a special graph. It's a special graph. What's special about it? Yeah? Give me one of the characteristics. What did you say? Oh, I'm talking about general trees here. I'm talking about general trees, of which this diagram is one. It really is a collection of vertices together with a collection of edges, and it has another set of particular characteristics. We're not quite to those special trees yet, okay? So there's something else that comes first. Okay? Yeah? Yeah. Okay, a tree is connected. It's a graph that is connected. Now, when I say that phrase, when I say that word, I don't mean that they, like share a spiritual connection or something like that. I have a very specific mathematical meaning, and that is a graph is connected if, anybody want to finish it? Or do you want me to do it? A graph is connected if, how do I know if a graph is connected? I'll give you a hint. My hint is to circle a pair of vertices. And then to tell you it doesn't matter which pair I circle. So a graph is connected if a path between every pair of vertices. That's right. So between any pair of vertices, there exists a path. Okay. In contrast, if there is a pair between which there is no path, they're not connected, right? Ah! All right. How about the other characteristic? You have it, Mark? Acyclic. Yeah. It's a connected acyclic graph. Now, let's talk about what acyclic means. So I'm going to build one that is not acyclic. So there, I added an edge, and now our graph is not acyclic. What's a cycle? And again, I'm going to ask you to think about characterizing it by looking at a pair of vertices. What's a cycle? Yeah, Nick? Oh, that's interesting. So a path that starts off with one vertex and somehow gets back there without traversing an edge more than once. Sure, that seems okay to me. Whoa, excuse me. Yeah? Right, exactly. Very good. Another way of characterizing, so that was a fine way. Another way of characterizing it is there is a pair, a special pair of vertices between which there is more than one path. Between which there's more than one path. Okay, because look at between 3 and 5, I could go this way or I could go this way. If you put those two paths together, you have what Nick suggested, which is this way of going away from a vertex and coming back to it. Okay? Now, think about what this means. If a graph is acyclic, it means that between every pair of vertices, there is less than two paths. And in a connected graph, there is greater than or equal to one path between every pair of vertices. So what does that mean for paths in trees? Yeah? Yeah, look at that. Between any pair of vertices, there is exactly one path. Hey, we just did a theorem, right? And proved it. Right? Ooh, who knew? That was kind of fun. All right, well, that is an aside. That is an aside designed to reawaken all of the thoughts that you had about trees from 173. Don't know. Okay. But it's also not particularly relevant because we're not going to look at general trees. That's a conversation we would have in the context of general trees. Instead, we're going to look at a very special kind of tree. Specifically, we're going to pull out a special vertex and call it a root. We're going to call it a root. We're going to direct all the edges away from that root. We're going to direct all the edges away from that root, which means that we have direction to our edges. In general, edges don't necessarily have direction. In our trees that we're about to study, in our special ones, they are directed. We imply that direction by the way we typically draw these things. 1, 2, 3, 5. And there's one more characteristic here. So far our trees that we're going to study next are rooted and they are directed. They are also ordered. And by that, I mean that this tree is not equal to this one. That the order in which we draw or represent the vertices adjacent to the root they matter. Okay, they're relevant. Okay, so these more specific trees that we're going to study are actually rooted, directed, ordered trees. All right, any questions about that before we start? I'm going to remind you that Lecture Helper is available to you. Forgot to remind you. Okay. All right. So before we actually start talking about the substance of the day, I want to show you possibly my favorite example tree that I've come across while designing the material for this course. Raise your hand if this tree evokes warm feelings for you. Do you see what it is? These are all the Mario games. Yeah, is this incredible? And moreover, Mario Galaxy is like a decade old. Oh yeah, 2007. So I'm pretty sure there have been lots of, like, is Mario Kart even on here? I don't know. The Mario series, the Mario family line died out in 2007. Is that true? I don't know. Can't be. Anyway, so now raise your hand if you have played one of the games on this tree. Okay. I have. This is why I love it. So you have all played a game, and I'm guessing here, it may not be true, but I'm guessing that the games that you have played on this tree are down toward the bottom of it, right? I don't know when Mario Kart came out. But that's the one my kids still play. But guess what? The only game on this tree, well, no, it's not true the only, but pretty much the only one of these games that I spent any real quarters on, time on, is this one. Way here. This tree connects us in a way that I never would have expected. And it connects everyone in between us, right? Like, everybody has played some of these games sometime during the decades in between Donkey Kong and, whichever ones you have played. So I like that there is this connection. All right, so that's Donkey Kong. That one is Donkey Kong. And I want to go even a little farther afield here because there's a movie that I need to recommend. That movie is called King of Kong. It's a documentary. It's a documentary about people who play Donkey Kong professionally. And it was made possibly 5 years ago. So there are still people who really, take very seriously their skill at Donkey Kong, and it's really a good documentary. It's hilarious. Like, I know those people. Okay, but that's not what we're here for today. Except I'm always looking for good movie recommendations, so I assume you are too. And I'm not even kidding. It really is good. What I really want to know is, suppose that somebody came to us and said, could you please build me a search engine for the Donkey Kong games, for the Mario games? And my question is, how would you do this in such a way that you can maintain the connectivity of the structure? So that, for example, we would know that the story of these two games is derived from this game. How could we keep track of that? What would memory look like? And really, this is the question. We're starting it from scratch. Go. What should we do? I want to build a search engine on this data in such a way that I can say, give me all the games that, where Mario is, where the gorilla exists. Yeah? You could do recursion down each branch. That would be a perfectly reasonable thing to do. And what I want to know is, what are the branches? What are the things that we're going to look at? Yeah? Where do we even store the games themselves? Yeah? Good idea. Really good idea. So the idea is that we create an object, say, that describes a game. I might call it a game node, maybe. as kind of a hint. I might call it a game node. And one of the things that that game node might keep is a list of, or an array of, game node pointers, right? So, and those nodes would point to other game nodes. Okay, that seems perfectly reasonable to me. In which case, we could ask all kinds of questions like, print them all out. Like, I don't know, give me a list of the games that were developed after the year 2000. Things like this, if we know how to get around in this structure, we could do. All right, so this is actually going to be the substance of the next 3 weeks or so, and it's going to be this balance between describing something mathematically and implementing it in such a way to make it work, and then furthermore, analyzing how well we have done. Like if we can argue that our algorithms are as good as possible. Are there any other ideas about implementing this thing? Seem okay? So it feels to me kind of like, I don't know, kind of like a linked list, but where there's branching, right? You've got a node and some pointers. Okay, that's fine. So that's kind of toward the implementation side. I want to revisit the CS173 background of things as we go forward. And the way I want to do that is just to have you play around with this given tree, answering these questions. So when a definition is important for us to get right, I will redefine it for you. Okay, I will redefine redefine all the key terms for you in context. But I assert that we don't have to do it carefully now, because if I did so, number one, you'd fall asleep. And number two, I think that the names themselves actually communicate enough about what these terms mean. So I've given you some of the key, vocabulary words associated with these rooted, directed, ordered trees. And I want you to answer these questions showing me that you know those definitions. Now I should say though, that in the first two of them, for general trees, that's for not rooted, directed, ordered trees. Okay, those first two questions are just for normal connected acyclic graphs. So, oh, here we go again. What did I say? All right, fine. Thank you, Cortana. Hey, Cortana. Stop. No, it's gonna, no, don't stop. Don't search. Okay. Hey, guys, go ahead and answer the questions. I'll argue with Cortana. Maybe I'll have to take her to the divorce court in Texas. I don't know how to. Cortana. Hey, Cortana. Okay. How are you doing? Do it real fast. How's it going? Silence. What's the longest English word you can make using the vertex labels in the tree? Bag. I can make bag. Can anybody else make something? What? Big head. Big-headed. Oh. That 2 words. I'm giving it to you. About I was going to say baggage, but that's the same. B-A-G-G-A-G-E. Oh, it's the same as big-headed. Baggaged. Big baggage. All right. The whole point of this question is, do you know what the vertices are? Maybe we should move on. All right. Find an edge that is not on the longest path in the tree. And give it a reasonable name. I named it Fred. Not a reasonable name. Okay, which edge is not on a longest path in the tree? Yeah, Mark? Ah, very good. Okay, so the observation here is that path is essentially the distance in number of edges, which will come up later, between any pair of vertices. So there's a whole bunch of ties here. In fact, how many longest paths are there? Longest paths of distance 6 are there? 4 of them, that's right. The only one that's not on, the only edge that's not on some longest path is this one, and a reasonable name for it is edge AB. In the undirected case, we could easily have called that BA instead. Also perfectly reasonable. Point being that we usually will identify an edge by its endpoints. There's an exception to that we'll see later. All right, one of the vertices is called the root. Guess which one it is. Please just say it. Okay? Make an English word containing the names of the vertices that have a parent but no sibling. Okay, so what are those vertices? I think B has a parent but no sibling, yes. Okay. G has a parent, D, but no sibling, and H is the only other one. I found this surprisingly difficult to come up with a word that contains B, G, and H. Bough like the branch of a tree. Huggable is my favorite one. It's sort of shockingly hard. All right, how many parents does each vertex have? How many parents does each vertex have? Same answer for all of this, except, okay, every vertex has one parent, except for the root. In this case, A. All right, which vertex has the fewest children? It's a tie again. List them out for me. E, F, I, J. Very good. In fact, how many children do each of those vertices have? 0. They have 0. We have a special name for such vertices. We call them leaves. So I'm going to go ahead and fill this one out now. J, I, no particular order. And I'd like to note that this is the moment where you go, wow, these trees are upside down, right? The root is at the top, the leaves are at the bottom. That's nuts. That's why I drew that. That's why I put the art upside down on the first page. All right, which vertex has the most ancestors? Again, there will be a tie. the most ancestors, I and J. I'm going to circle those ancestors, the common ancestors between I and J. And I'm going to ask you, so those are the common ancestors between I and J. I'm going to ask you, how many ancestors does J have? How many ancestors does J have? There is a key question. What's your puzzle? Okay, I'm asking about J. 1, 2, 3, 4, 5. The whole question is, am I my own ancestor? Is J its own ancestor? It makes sense mathematically to say yes. So a vertex is its own ancestor. But so as to avoid off by one errors in the rest of your life, you'll always want to look or ask if it's in the context of solving a problem, is a vertex its own ancestor? Okay. So in our case, we'll say yes. Okay, any question about that? Okay. Let's see. So what I've circled is a set of common ancestors between I and J. They both have the same number of ancestors, but their ancestor set is not the same because they each play a role in their own. Let's see. I was going to say something. Oh. Are there any questions about the whole ancestor thing? Is it okay? All right. Which vertex has the most descendants? The root. And how many does it have? In this case, 3, 6, 9, 10, right? A vertex is an ancestor of itself. It has 10. And then finally, list all the vertices in B's left subtree. Now, which way is left, right? Wait, which way is left? It's as you're looking at the tree. So B's left subtree is on that side. So B's left subtree contains vertices C, E, and F. Okay? So don't try to identify with the vertex because that's the right subtree. This is the only moment where we've actually talked about the ordering of the structure, where left subtree and right subtree are something different. All right, so I've actually been lying to you. I apologize. Again, this is a difficult trust relationship, I think, because we're actually not just going to talk about rooted, ordered, directed trees. We're going to talk about rooted, directed, ordered, binary trees. From now on, I'm just going to refer to them as binary trees. The substance of that definition simply says that any given node can have at most 2 children. So in fact, that Mario tree that we looked at, the Mario family tree, it isn't the kind of tree that we're going to talk about in great detail in the context of lecture. Actually, in MP5, you'll see one. Okay, so we're going to give a recursive definition of binary tree. It's totally simple. What I want you to kind of focus on is a symbolic representation of this thing. I'm going to say it pretty simply first. A binary tree is a root together with a left subtree and a right subtree. Okay? Or it's empty. Or it's not. So it's a root together with a left and right subtree, or it's not that. The only thing which is not that is the empty tree. So let me spell that out with some symbols and descriptions. So binary tree T is either empty, in which case we write T equal the empty brackets, or it's a root together with subtrees TL and TR, each of which is also a, not quite, each of which is also a binary tree. The symbols we use to write that are T equal R for the root together with TL and TR. Okay? So either tree is empty or it's not. If it's not, it has this three-part characterization. Okay, now look at what this means. It means that we can now describe the illustrated tree, right, given with symbols. We could use brackets and spell it out, right? I could say, I'll just look at this part of it for a second. I could say that this tree, the left subtree, is a root together with its left and right subtrees. Look, I've just described this. The right subtree is similar. It's a root together with left and right subtrees. And then the whole tree, T here, is that minus sign together with TL and TR, as I've described them. Now, I don't know about you, but I don't want to deal with trees in this symbolic form, right? Way, 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 way too many brackets. I'm gonna make bugs. So when I think about trees, I'm almost always gonna go ahead and draw the picture. They're just models for the same things. Now, this is not to say that this sort of parenthetic, this bracketed representation of a tree has no use. I believe it's syntactic parse trees in the natural language toolkit for Python that explicitly draws out trees using these tuples. It's pretty ugly. But nonetheless, all it's doing is creating different models for the same structure. Okay? Our code's going to be way more elegant than that. All right, so any questions? So everything you have described here, nothing you have described here is code yet. We've got a definition of a tree, which is largely symbolic. We've got a picture of a tree, which you kind of look at and you go, yeah, looks like a tree. Right? But we have no code. We have no representation in memory. All right, any questions before we go on? So one of the questions here is, doesn't a binary tree mean that each node must have up to 2 children? Meaning it could have only one subtree. So I want to address that question actually, because I think it's kind of interesting. I believe that the question is captured by this example. Okay, so here's a binary tree. And I want to describe it using the definition that I have above. Here's how to do that. Here's how my definition captures it. Look, this is a root together with an empty left subtree and a non-empty right subtree. So while it's true that this tree has only one child, I'm going to assert actually that its left child is an empty tree. That's what having an empty tree gets us, essentially. Okay? So I I don't know who I'm talking to. That's like the most disconcerting thing about this, is I want to make sure that I clarified the answer to that question. So our general definition that says a tree is either empty or it's this three-tuple thing, that captures the case where a node has only one child, because the other one is just the empty tree. All right. Any other questions about this? Okay. So this is the structure. Oftentimes we're interested in writing functions on the structure. And the cool thing is that the structure itself drives the definition of the function. That is, oftentimes the function itself will be a recursive function defined on the two different cases that you see here. So we're going to write a function defined on an empty tree together with a general tree, a non-empty tree. All right, so what does that look like? What's the function? Okay, so the function that we're going to talk about is simply the height. Now, this is going to turn out to be a very, very useful function to us, because a lot of our algorithms are going to depend on the height of a tree. So we're going to care a lot about the value of this particular function for algorithms that we write. Okay, so what's the height? Well, it's the length of the longest path from the root to a leaf. So in this tree, raise your hand with the height of this tree, the example tree. The height of this tree is either this or this. So it's ambiguous because I haven't really told you. Path length is the number of edges, okay? Not the number of vertices on the path. So the path length is the number of steps you would have to take if you could step over an edge. Yeah? You're still answering 3? So it's 3. The answer is 3. Yeah, you got it. So this one has height 3. Okay? All right, so now I want to draw a couple more for you. What's the height of that one, of that tree? 1, right? What's the height of that tree? Okay. What's the height of that tree right there? What is that tree right there? It's the empty tree, right? It's the absence of a tree. What's its height? Guess what? The English definition doesn't apply, right? Because there is no root, so we can make it be anything we want. The height of an empty tree can be anything we want. So what we're going to do, our plan, is to create a function for the height of a non-empty tree, and then choose the height of an empty tree in such a way that it helps us mathematically, okay? Because we get to do that because the English definition only applies on non-empty trees. But I want a definition that works over the same domain, that is, the set of all binary trees. Okay, so let's work on the general case first, the non-empty case first. So I want the height of the tree to be some function of the heights of the subtrees. So what does the height of this tree look like? So if t is equal to the root together with TL and TR, then height of t, and I'm going to truncate that, is what? Suppose I know the height of the left and the height of the right. How am I going to get the height of the whole thing? Yeah, I'm going to take the maximum of the height of the left and the height of the right. I'm going to take the maximum of them. So in that case, it's 2, because that's the maximum height of those two. And then I'm going to plus 1 for that level, right? So it's plus 1. Good. Very good. Okay. Now here's what I want. Suppose that T is the empty tree. Height of tree T is what? What do you want it to be? What's your instinct say it should be? It feels like it should be 0, right? But if we make the height of the empty tree 0, if we make the height of the empty tree 0, then what's the height of this tree? It's 1, right? Because the height of its left tree is 0. The height of its right subtree is 0. The maximum of those is 0. 0 plus 1 is 1. Ugh, darn it. So 0 isn't the right thing. So what are we going to make it? Yeah, -1, that's right. Good. So the height of an empty tree, we are going to define to be -1. Raise your hand if that bugs you. It doesn't bug you? Oh, good. Okay, we can. Does it bug you? Yeah, because it has no meaning, right? Like, what's a negative height? Like, does it dig down into the ground? What is a... Oh, wait, that is what a tree actually does. Wait, I don't know what a negative height means, right? But you know what? I don't know what an empty tree means either. It's the absence of everything, right? I can create any definition I want for this vacuous situation. And I'm going to create that definition in such a way that all of the real cases, the cases for the real trees for which I want height, is meaningful and is elegant. Now, if you would insist that I force the definition of an empty tree to be 0, I would have to have another base case. I'd have to insert then a base case for a single node tree. And then we would be okay. But I don't want to do that. I like it when you kind of minimize the number of cases. Again, the more special cases you have, the more complex the code is that you have to write that falls on top of it. Okay? All right, how are you doing? Is it okay? So what's the height of an empty tree? Yep. For our purposes, we will never see a case where the height of an empty tree equal -1 doesn't work. Okay. So there are 3 definitions that come all at the same time. 3 definitions that come, well, there are 3 definitions that are easily confused. They are full tree. The 3 definitions that are easily confused are a full tree, a complete tree, and a perfect tree. Now, I don't know where those 3 words live for you, but for me, they kind of all live in the same semantic spot, right? Full, perfect, complete. It's like the dream life. And so what I want to do is introduce them to you all at the same time, just so that you distinguish between them from the start, okay? All right, so the first one is going to be a full tree. This tree that I have given you is a full tree, and this one is not. Do you have any speculation on what a full tree is? So the one above is a full tree, and this one is not. Do you want to speculate on what a full tree is? Yes? You have to yell from way back there. Every vertex has 2 children or no children. That's right. That's right. So every vertex, oh, look.